There are multiple reasons for having multiple routing protocols in an organization. A common reason involves the acquisition of companies. Your company might use OSPF, and the company you just acquired uses EIGRP. Another reason is that you want to split up the routing domain because of administrative privileges based on geography, organizational structure, or some other reason. Another common reason requires the splitting up of a routing domain into smaller routing domains to accommodate routers with slower CPUs or less memory. Or it could be that you have hardware that doesn't support the routing protocol that you use. Some firewalls or load balancers may not support EIGRP or BGP. Now, when you have multiple routing domains, you will often need to provide end-to-end connectivity. But if you look at the topology we have shown, we have R1, R2, and R3 participating in EIGRP, and then we have R3, R4, and R5 participating in OSPF. When we look at R5, R5 does not have any of the networks that are coming from R1 or R2. And the same thing will hold true on the routes from R1. We do not have any routes from R3, R4, or R5. Redistribution of the routes from EIGRP into OSPF or OSPF into EIGRP is not automatic. But if we actually configure redistribution of EIGRP into OSPF or OSPF into EIGRP, as shown on R3, we can now see that we have the OSPF learn routes on R1 as indicated by the DEX marking, which stands for EIGRP external. Or we can also see that on R5, we have the EIGRP learn routes as indicated by the OE2 marking, which stands for OSPF external type 2. And now R1 through R5 has routes for every network within both routing domains. Now let's review some of the redistribution terminology. The first one is source protocol, and this is the routing protocol that provides the routes that are to be redistributed. The next one is the destination protocol, and this is the routing protocol that will inject the routes or receive the routes that are being redistributed. Now by default, when you talk about route redistribution, it is a one-way redistribution. In this case, it is the source protocol that is injecting routes into the destination protocol. But sometimes you might want to have the destination protocol inject the routes back into the source protocol, or they could be different routes for that matter. In that case, we will refer to that as mutual redistribution. So in this case, we have OSPF that is redistributing routes into BGP, and then later on, we also have BGP learn routes that are being redistributed into OSPF, and this is known as mutual redistribution. And now let's talk about some of the source protocols. So with source protocols, we have various different options we can choose. We have static, which is static routes, and this is any static route that's present or installed into the routing information base or routing table. Now static routes can only be a source. In addition, we also have connected networks, and this is any interface in an upstate that is not associated with a destination protocol. And again, connected networks can only be a source routing protocol. And then we have RIP, which is any routes that's in RIP, including any RIP-enabled networks. And then we have EIGRP, which is any routes that are learned in EIGRP, including EIGRP-enabled connected networks. And then with OSPF, it is any interface that is enabled within OSPF or any OSPF networks. Now, one thing to note is external OSPF routes will not be redistributed into BGP unless you use the optional keyword of match external. And then we look at ISIS, it will take any routes within ISIS except for those that are locally enabled interfaces. So it'll basically be the routes that are learned from other routers, but not any of the routes that are actually installed locally because they're connected networks and enabled on ISIS. And then when we look at BGP, it's any route that is installed into the BGP lock rib table that is learned externally. Now, one thing to note is if you use internal BGP routes, you must add the optional redistribute internal keyword because typically this is used as a loop prevention mechanism. And then the configuration occurs in the destination protocol. The source protocol and options are configured as defined in the destination protocol with the command redistribute, and then you're going to choose your source protocol of either connected, static, EIGRP with the autonomous system number, the OSPF process, or you could choose ISIS or BGP. And then depending upon what you choose for routing protocol, there could be sub options. So if you look at, take for example, OSPF, there's a sub option of match external or internal with a type 1 or type 2. And if we look at ISIS, we have an option of level 1, level 1.2, or level 2. But the command structure overall is generally it's the same. And then there is some things that do vary based off the destination protocol, which would be the destination protocol options. Now, there are some common rules that you must understand when we talk about route redistribution. So in the diagram, we have two routing protocols configured with mutual redistribution. The EIGRP route redistributes into OSPF, and OSPF redistributes into EIGRP. Now, if we add a third routing protocol like BGP and configure mutual redistribution between BGP and OSPF, the 172.16.2.0 network is redistributed into BGP. But the 172.16.1 network, which was learned in EIGRP and then redistributed into OSPF, does not redistribute into BGP. And then the same thing will be BGP's 172.16.3, which was redistributed into OSPF, will not redistribute into EIGRP. And this is because redistribution is not transitive. To solve this solution, what we will do is we will add mutual redistribution between EIGRP and BGP, as shown here on this upper link. And once we've done that, then the 172.16.3 network that BGP has will redistribute into OSPF as well as EIGRP. And then EIGRP's 172.16.1 network will redistribute into OSPF and BGP. Now, sequential redistribution is allowed. So if we look at the topology we have here, we have sequential redistribution from one protocol to another protocol, which is spread across multiple routers. And this again is allowed. So when R2 learns the 192.168.1.1 network prefix, it can then redistribute those routes into BGP. And then when R4 learns the 192.168.1.1 network prefix via BGP, it can redistribute that route into OSPF, which is then advertised to R5, so that R5 will then have the network that is installed. And again, sequential redistribution is perfectly allowed. The next comment is seed metrics. Now, redistribution causes a loss of path information. So components for best path calculation in one protocol are different than another protocol. And seed metrics are used to help inject some path information from the source protocol. Now we look at EIGRP. EIGRP starts off with the seed metric of infinity, which basically means that we will not install this route into the EIGRP topology table. With OSPF, OSPF will set all routes to a type 2 external. And OSPF type 2 external is the least preferred type of external routes, whereas a type 1 external is more preferred over a type 2 external. Now, routes that are sourced from BGP will have a seed metric of 1, while all other routing protocols will use a seed metric of 20. And then with ISIS, all routes will receive a seed metric of 0. And with BGP, the origin is then going to be set to incomplete, and the MED, the multiple exit discriminator, will be set to the value of the IGB metric. The next rule is that the route must be in the RIB for redistribution. So in our topology, RIB is going to be enabled on R1, R2, and R5. And then R5 is going to redistribute that route into EIGRP. Now, if we look closer at R6's routing table, you'll notice that we have, on the 10.13.1 network, a route that exists on R6. So everything appears to be working properly. Now, another network engineer has enabled OSPF on R3, R4, and R5. At this point in time, users have now reported a loss of connectivity to the 10.13.1 network, and those are the users that are attached to R6. So let's go back on R6 and see what we can find out. And you'll notice that we no longer have the 10.13.1 network. It's disappeared. So where did the 10.13.1 network go? Well, let's look at the routing configuration on R5. So if we look at R5 within the EIGRP, we have some default metrics set up and established, and we're redistributing RIP. Nothing has changed on R5. The only thing that's been done is we've enabled OSPF on the link right here. Well, if we actually look at the 10.13.1 network on R5, we'll notice that the network is now learned through OSPF. It's no longer being learned through RIP. And because the source routing protocol is no longer in the routing table, it can no longer redistribute that route. And so what the solution is we need to go back to R5, and now we need to configure to redistribute OSPF into EIGRP, because the 10.13.1 network exists in OSPF, which has a lower administrative distance of 110 versus RIP's administrative distance of 120. And once we do that, when we log back on R6, you'll notice that we now have the 10.13.1 network. So this provides an overview as far as why we actually would redistribute routes and some of the common rules with redistribution.